So, B part 4, lecture 9B, harmonic oscillator. Then I will show derived for the Hamiltonian constant of motion, condition for constant of motion. Now, you see, lecture 9A, I repeated it twice, 9A and 9A. So H is a function of Q of t, P of t. Attention now, this case, the Hamiltonian is, this case, autonomous. So that's why t does not appear explicitly on this Hamiltonian here. Now, see, we derived that p squared to m 1/2 m or omega squared q squared. You just look at lecture 9A, where Q is a generalized coordinates. You see Qi, I is equal 1 to M, and P is canonical momentum conjugate to Q. Pi, this is downstairs, you see? I is equal 1 to N. Now, Hamilton equations for any system are Q dot I, I'm sorry, this I is upstairs. Q dot I is partial of A respect to Pi, and P dot I is minus the partial derivative of H respect to Qi. This we derived, you see, from previous videos. Since you are in 1 degree of freedom, just one equation, you have two variables here. So for I is equal 1 to compute. Step 1, partial H with respect to P is quite easy. You just look H here and take the derivative, partial derivative with respect to P. Remaining Q constant. So just derive over there and write down here. This implies that Q dot is P over M. Attention now. From the Hamilton equation, partial H with respect to P is, this case, okay, is Q dot, okay? This is Q dot, is P divided by M. Step 2, derivative of H with respect to Q. You just go over here, P, this case, Q is a variable and P remains constant. So derivative here with respect to Q is 0, so just take the derivative of Q squared respect to Q. Then it's a straightforward derivative. So this case is M omega squared Q, you see? And attention now, partial H respect to Q, this is equal, this case, P dot. That's from Hamilton's equation. And then you just write down Q dot P of M, and P dot is minus M is omega square Q. Let's increase here, this omega square. Now, you see, let's move to step 3, just for you to see clearly that step 1, step 2, and this is step 3. Condition under which the Hamiltonian is a constant motion. Now, you already derived this, so H is a function of Q and P, not function explicitly of T, time. That's why this is a non-autonomous system. So just to take the derivative, dH of dt, and this is clear that this Q dot over here, which is dq dt, this is exactly partial H respect to P. You copy here from here, you see? You just substitute over there. And now this is partial H respect to P. P dot is dP of the t, derivative of P respect to t. Now just to substitute also, look at here, and substitute right over here. So this will cancel because this minus here reach this plus here. So this is a same symmetric terms. So this leads to the total derivative of h respect to t is 0. We can conclude that the Hamiltonian H is conserved along the motion, along the trajectories. Now, step 4, that's mark here. This is step 4. Geometrical interpretation. Since the Hamiltonian P is constant along trajectories, the particle moves on the curve in the phase space. You see, the phase space is determined by H QP is equal E. E is the total energy which is constant for this problem here, okay? For the harmonic oscillator. So E is constant, okay? Kinetic energy plus potential energy, this is constant. So I can substitute and plug, you see, this sum over here, which is quite clear, okay? This is kinetic energy, this is potential energy equal to the total energy. Now this little algebra, you see, manipulation of little algebra, you just write P divided by M times 2E. I call B squared. And Q squared divided by 2E divided by M on squared. This I call A squared. This is equal 1. So then I can substitute A squared and B squared and write down over there. So Q squared by A squared plus B squared by B is equal 1. So this is the equation of the ellipses. So A here, you just take the square root. You see, A squared, you take the square root and write there. And B squared is this, so B is square root of 2ME. See, easy. Thus, the trajectories are ellipses in the phase space. What is phase space? Phase space is also can be called cotangent space. Don't forget that. So semi-major and semi-minor axis determined by the total energy E, mass M, and frequency om. So this the ellipse you have, you see the semi-major and semi-minor axis. You see, as E increases, now you can manipulate it. Okay, this constants. Okay. E is constant, so if E increases, the ellipse gets longer. That's longer, you see? So increases the major axis. Then, if M or W change, the shape, aspect ratio of the ellipse also changes. So this is some, you see, you just can, this, impose this, and this you can go to the computer, okay? And then you can manipulate all these major axes, minor axes with the numbers and see what is written over here. So that's a geometric interpretation of this problem here, which the Hamiltonian, the constant of motion of Hamiltonian, the trajectories, they are ellipses. See, that's it. That's one application. A second example, okay, applied to constant motion. That's it.